All right, we're going to be doing Alien Dictionary using Kahn's algorithm, which is basically a breadth first search. So they give us a list of words, and these words are in alphabetical order. But it's not necessarily like an English alphabetical order. We assume that it's like in some alien language. So if we just look at these first two words, WRT and WRF, the first difference in these two words is T and F, which means that because WRT came before WRF, that means that T is less than F in this alien alphabet. So what we're going to do is we're going to create a directed graph, and then we're going to run Kahn's algorithm on it. Kahn's algorithm, if you're not familiar with it, all it does is it processes the nodes with no edges, no incoming edges, and then it removes those nodes edges, uh, those nodes outgoing edges. So so we process the nodes with no incoming edges, and we remove those nodes outgoing edges, and then we just keep repeating this over and over and over again. So for example, if we had the graph A points to B points to C, we would start, and then let's just put something else in here. Let's say X points to, I don't know, what's a good letter, E? Okay. Oh, I didn't put the C in there. Okay, so we have A pointing to B pointing to C, and then we have some other component of the graph that has X pointing to E. So what we would do is we're going to take the nodes A and X, process those, and then remove those edges. And then we'll process B and B, trying to highlight B and E, then we'll remove those, and then we'll do C, and then we're done. And if we're able to do that, that means that we have a valid topological sorting. And if you don't know what a topological sorting is, it's just returning an array of nodes where all the nodes come before all the nodes that they led to in the graph. So for example, in a valid for this example, a valid topological sorting would be A, B, C. So A has to come before B, and as well as C. B has to come before C. So this would be a valid so far, and then X would have to show up before E. So we could do ABC XE, but another topological sorting that's also valid would be XE ABC, because you could think of this as like, let's say this is, I did this example in the last video, but like this could be heating up oatmeal leads to, and then this points and then after we heat up our oatmeal, we can eat the oatmeal. And you could think of, say, this as, I don't know, straightening hair, and then after you straighten it, you hairspray hair. So we could heat this, like these are like independent of each other, right? Like I can heat up my oatmeal and eat it before I straighten my hair, or I could straighten my hair first and then heat up my oatmeal and eat it. So it doesn't matter. That's why it doesn't matter like what order we put those components in. But anyway, that's what topological sorting is. So Kahn's algorithm, let's just start coding it out. So I'm gonna leave this here because I might use it again. So we need the number of edges pointing to nodes. So we're gonna call that in degree, which is the number of incoming edges for every node. And we could just go ahead and make this size 26 because we're only dealing with lowercase English letters. So 26 will work just fine. And now we need to make our adjacency list. So let's do that. It's a list of characters. So this is going to represent our graph. I'll just call it adjacency list equals new hash map. Cool. And then we're going to loop through every word and loop through all the characters in those words. Cool. And we want to just say adjacency list dot put word dot char at I. So we're putting, for every letter, we're going to add an array list. Cool. Now we have an empty adjacency list, and now we need to populate the edges in this adjacency list. So we're going to loop through every word again. Actually, we need an index for this, and I'll explain why in a second. We're going to say I equals 1, I is less than words dot length plus I. And what I want to say here is, okay, so in order to check if like what letters come before which letters, so like let's say I have the word cat, and the next thing in the dictionary is say cat, I don't know what's a good cab. Okay, so if in our dictionary we have cat and cab, well, and let's pretend this is the words that we're given, right? Or so this is words. Words equals this. I'm just giving you an example here. So the first difference between cat and cab is the T and the B. So that means that T would be before the B in this alphabet. So we just want to find the first difference in these words, two at a time. We're going to compare two words at a time, find the first difference, and now we know which letters lead to which letters in this directed graph that we're building. Okay, so we are going to say, let's just say, I'm going to write a helper method. So character, we'll call it difference equals new pair. Oh no, not new pair. I'm going to call helper method. So get difference, and we're going to pass in words at I-1 and words at I. Cool. And so what I'm going to do here is I'm going to get the first difference between these two words. So that'll be these two characters that I'm returning. And then if, why is the spacing off on this? Okay. Then if the difference is not equal to null, so that's assuming that we found a difference. If the difference isn't null, then we need to put that in our adjacency list. So we need to get difference.get key. So it's going to get the first character in our pair. And then we're going to, so we're grabbing the array list here. So adjacency list.get, get the array list for this character, and then add in the difference.get value, which would be the second character here. So we're just creating an edge between these two characters in our adjacency list. And now, if the difference is null, then we need to check that the first word that we checked, basically we're checking if the first word is, if it's greater than, in terms of, so we're checking the length. So if the length of the first word is greater than the second word, that's not a valid input. So we just need to return an empty string. Because for example, like cat and catfish, if we look at, let's just pretend this is English. In a normal dictionary, when there's no difference between like the minimum of, so the minimum length here would be 3, right? So we check the first 3 letters here, and we check the first 2 letters here. There's no difference between cat and cat. So that must mean that the longer word has to appear second in this list of words. But the problem is what if there's no difference and the longer word is first? Well, then that's not a valid, that's basically not a valid input. So that's why we're going to return an empty string here. I'm just checking if that first word is longer. If it is longer, then return an empty string. Okay, cool. Now, okay, so we populate, okay, so now we got to write this get difference method. So to find the first difference in the words. So we're going to say private pair character get difference, and it's going to take in S1 string S2. Okay, and we are going to find the minimum length between the two. So this is going to be math.min of S1.length, S2.length, because we only want to loop through the minimum length of the both of them. So for int I equals 0, now we're going to loop through all the way through the length. And if we find a difference, just return it. So s1.char at I is not equal to s2.char at I. Then return the difference. So this would be s1.char at I and s2.char at I. Cool. And we return null. So we just, as soon as we find the first difference, we're going to return it. And then if we never find a difference, we return null to say that there is no difference. Okay. And now, so we populate our adjacency list. Now we can actually start Kahn's algorithm. So we need to create a queue because Kahn's algorithm is essentially a breadth first search. So how do we do a breadth first search? We create a queue. So there's going to be a queue of characters. We'll call this queue equals new array dequeue. Did I spell that right? No. Okay, cool. And what do we want to put in this queue? So we want to loop through, actually, shoot, for in degree. Yeah, okay, so we want to loop through all of the nodes in our adjacency list. And then we want to check if they have 0 edges using our in degree array. So I want to say for every character, so for every letter in adjacency list.keyset, because we added up here is where we went through all of our words and all the characters in those words, and then we map the letters that we found in our list of words to an empty array list. And now we're just going through those letters here. So for every letter in our key set, then we want to check if in degree of the letter minus a. So this is letter A. This will be index 0. Oh, we didn't populate our in degree. Let's do that really fast. So that should have been right here. My bad, I forgot one little step. So we populated our adjacency list, but our edges in the adjacency list, but we didn't actually increment the number of edges in the in degree, in our in degree array. So this is going to be, okay, so this is saying that this is an edge to this letter, or this node is pointing to this letter. So that means that this letter here has an edge. So we're going to say difference dot get value minus a, and we're going to just increment that. Cool. So we incremented our number of edges for that second letter, because it now has one more incoming edge, right? Okay, so back to this. So we're looping through all the letters in our key set, checking if that letter has 0 incoming edges. If it has 0 incoming edges, then we're going to put that in our queue. So let's add the letter, and now we can start our breadth first search. So while the queue isn't empty, whoa, why did technical difficulties? Okay, so while the queue isn't empty, we want to, what's actually next? Shoot. Well, obviously we want to pull the thing out of the queue. So let's just grab the character letter equals queue dot pull. Cool. So we pulled the letter, and then we want to go through all the neighbors of this letter, and we want to decrement. So remember, what's our algorithm up here? Let me just copy paste this so we can remember what we're supposed to do. So process all the nodes with no incoming edges. So that's what we're doing here. We're going through the queue of our queue has all the nodes with no incoming edges. We're going to pull them out, and then we're going to remove those nodes' outgoing edges. So we're going to go through all the neighbors. So first we're going to check if the adjacency list that contains key, if it has this letter, then loop through, let's see, character, I want to say neighbor. So for every neighbor in adjacency list dot get letter. So I'm just looping through all the neighbors of this letter here. Okay. And then I want to decrement the in degree of the neighbor, because I'm removing the edge from this letter to these neighbors. And yeah, so we take the letter, subtract it from A to get an index into this in degree thing, and then we decrement the in degree. All right, so then, so now we want to check if that in degree hits 0. So after decrementing it, so we decrement first, and then we check if it has 0 edges now, this neighboring node has 0 edges, we want to put it in our queue. Right, because we're repeating this step. We remove the outgoing edges, and we process the nodes with no incoming edges. So if this has no edges, if this has no edges, we need to add it into our queue to process that node now, because it has no incoming edges. Okay. Now, and then, okay, so we need to, so we're doing our Kahn's algorithm, right? But we also need to return the topological sorting. So we're going to create a string builder. Equals new string builder. And this is just going to be the size. I'm just passing in the capacity as an optimization. So this is going to be the size of the adjacency list. This is holding all the letters that we found in our list of words. And what we want to do is when we queue out the letter when we pull out the letter from the queue, we want to put that into our string. So we're going to do sb.append letter. And let's see, I think we're good. We can just go ahead and return. We can return sb.toString. So this is our string builder. We're converting it back to a string, so we return it. But we need to make sure that we were able to get through all the nodes when we were doing Kahn's algorithm. Because if we weren't able to, so like in here, when we're pulling out of the queue, if we weren't able to pull all the nodes out, then that means that we have a cycle, that at some point when we were going through the neighbors, that there's some nodes that had, basically all of the nodes had at least one incoming edge, so we weren't able to get through all the neighbors, which that can only happen if we have a cycle. So we need to check if q.size, no, not q.size, if actually we can just keep a count. Let's do that. So int count equals 0, and then we'll just say every time we pull out, we'll just increment the count. And if the count is equal to the adjacency list.size, because again, adjacency list was holding all the letters that we found in our list of words. So if the count equals adjacency list.size, then we can just return the string builder.toString. Otherwise, we return the empty string because we found a cycle. Okay, so return or run it. Let's see. Index out of balance exception. Where did I go wrong? I is less than words dot length. What? Oh, this is word dot length, not words dot length. So we're going through the string here, right? Okay. So let's run that again. Cool, and it runs. Let's submit it. All right, and we're done. So that's how you do this problem if you want to use solve it doing Kahn's algorithm, so or breadth first search, whatever you want to call it. So yeah, thanks. And, let's go over the time complexity really quick. So really fast, this is O of W for the list of words, and then in here we are going through all the word lengths. So that's going to be O of W times the average word length, right? Because all the short words and long words are going to average out to some average word length. So that'll be the worst case. And in here, this is also going to be O of W, but get difference is also, so if we look at get difference, this is also looping through the words, well, the minimum of the 2 words length, but eventually it'll loop through all the word lengths, right? So this is going to be the same thing, O of W times the average word length. Okay, and now let's look at, is there anything else in here? Anything else of noting, worth noting? This is going to be O of 26 at the most, so I won't even go through that, right? Because there can only be at most 26 letters in our adjacency list. Then the breadth for search is just going to be O of V plus E, which V here would be, let's just write that. So O of V plus E, where V is the number of unique letters that we found in our list of words. So this whole thing is going to be big O of W times the average word length plus V plus E. And, E is obviously the edges between those letters, right? Okay. Space complexity, let's do that really fast. So that's just going to be O of V plus E because of the adjacency list, so V plus E. Because, right, the adjacency list is holding all the unique letters, which is V, and then all the edges between those letters, so that's O of V plus E, and yeah, I think that's the biggest factor. Okay, cool. So this is our space. This is our time. If you like the video, you can give it a thumbs up. You can subscribe. Cool. Bye.